considering the deformation of a fluid as it moves, and we answered a particular question. We took two fluid points, position at x and a nearby position x plus delta x. This defined for us the separation vector of the two fluid points, and we asked the question, at what rate does this separation change? That is, this vector separation. So, if you wait at time delta t, one of these points, each of these points will move to a new position, and we then obtain a second separation vector, which I called delta x dashed. I calculated the coordinates of each of these two new positions in terms of the old positions and the velocity field of the fluid, and we arrived at the result of the rate of change of the separation vector x is given to us by delta x dot nabla on the velocity field of the fluid V. And I said to you that this is the seminal relation from which we will prove a number of results, a number of very important results. Alright, why are we considering the rate of change of separation? Well, the answer is because the rate at which the points separate is determined by, in particular, the rate at which you need to supply energy to perform this separation of the fluid points. In other words, energy must go into the flow in order to cause these individual fluid points to separate at a particular rate. The first thing that I want to do now is to calculate a number of familiar quantities, familiar from your first year study of elasticity in the physics that you did, elementary physics. You defined a strain, for example, when you were dealing with cables and the stretching of cables. You also defined a shear when you were dealing with the deformation of solids. And what I want to do now is to calculate the equivalent quantities for fluids. So let's begin with the linear strain rate. Let me refresh your memories as to what you define to be the strain. Here we're interested in, if you like, the material that joins the 2 points, and the strain in elementary physics is defined as the final length minus the initial length divided by the initial length. And the symbol for strain, I think, that you used was E. That is the customary one. It may have been an epsilon. That is basically the definition that I wish to apply in order to calculate the linear strain rate of the fluid. So what I'm going to do, I've calculated an answer here for the rate of change as the fluid moves of the separation vector. I'm going to write the separation vector in terms of the length of the segment of material that lies between the 2 points. So I'm going to put delta x equal to delta L times n hat. N hat is it's the unit vector in the direction of the point of interest. and in the diagram that I have, I position myself as a wet observer at the fluid point which sits at position x at time t. I am looking towards the point, the fluid point that sits at a nearby position x plus delta x, and so my unit vector that I'm talking about over there is the one in the direction of that second point. Delta L is then the length of the vector delta x. So this is the initial length of the fluid segment that we're considering. Now, of course, I could go through a very similar argument to the one that I used yesterday, but that would be reinventing the wheel, and you don't want to reinvent the wheel every time you want to travel from one place to the next. So what I'm going to do is I'm going to apply this result to this problem. I'm interested in calculating the rate at which delta L changes. So let me get down some definitions. So we want the strain that develops in the segment, this material segment, in time delta t, is going to be equal to, and it is the final length, delta L dashed, times delta L, divided by delta L. So that is the strain that I want to calculate. This is the strain that develops in time t. I'll call this strain. I don't want to multiply symbols because I want to reserve the symbols for what I do afterwards. So that is the definition of the strain. So the rate at which the segment is straining is strain over time taken for the strain to develop, and that is delta L dashed minus delta L divided by delta L divided by delta T. And I will write this as 1 over delta L dashed minus delta L over delta T. So in the limit, as delta T goes to 0, we get that the strain rate is equal to, well, it's 1 over delta L. That doesn't change. It's the initial length of the segment that I'm considering times the limit as delta T goes to 0 of delta L dash minus delta L divided by delta T, and this gives me 1 over delta L dL d by dt of delta L. So that's the quantity that I need to calculate. The result that I have tells me what d dt is, not of delta L, but of delta x. So let me see what I can do with this result here. But d by dt of delta x, which is equal to, according to that result, delta x dot lambda on d gives, I'm going to substitute now the relationship that relates the vector separation to to the length that I'm interested in, and this gives me d by dt of delta L times n hat is equal to delta L n hat with lambda on d. It's the quantity on the left-hand side that I must now rearrange. Apply the product rule, and this gives me that it is d by dt of delta L times n hat is delta L d by dt of n hat. Well, that's nice. I've got the derivative that I need. The factor of 1 over delta L, well, I can multiply and divide both sides of this expression by delta L, and that will then give me the quantity that I need as one of the terms. So dividing by delta L, what we get is that 1 over delta L d by dt of delta L multiplied by n hat is plus, and that delta L cancels, d by dt of n hat, and that is equal to the other side divided by delta L, which is n hat dotted with lambda b. So here is the quantity that I need. That is my linear strain rate. How do I isolate it from this expression? Well, let's see now. The second term, I want to get rid of that because I don't want the rate at which the direction is changing. I may, in different contexts, want to know that, but for the moment I don't want to know that. But n hat is a unit vector, isn't it? And here we have a derivative of the unit vector field. So make use of this fact. N hat dotted with n hat is equal to 1. And therefore d by dt of n hat dotted with n hat is equal to 0. And if I now do the derivative on the left-hand side, I get to d by dt of n hat dotted with n hat plus n hat dotted with d by dt of n hat is equal to 0. Ah, yes, but the dot product is symmetric. A dot b is the same as b dot a. And so this gives me twice this quantity is equal to 0, and therefore n hat dotted with d by dt of n hat is not. In other words, the vector that you get by differentiating n hat is orthogonal to n hat, right? The rate of change of direction is always in the direction perpendicular to the unit vector. So, yes, this is the result I had. Oh yes, but if I dot this equation with n hat, I get rid of the unwanted term. And so what this means is that 1 over delta L d by dt of delta L, and this is n hat dotted with n hat plus n hat dotted with d by dt of n hat is equal to n hat dotted with, and you must use brackets now because otherwise you will get a confusion, and it is n hat dotted with n hat dotted with lambda acting on b. This is 0. This is 1. And so I have succeeded in isolating precisely the quantity that I want. And this is now my result. The rate at which the fluid strains is equal to n hat dotted with n hat dotted with lambda acting on the vector field V. I'll examine what that quantity on the right-hand side looks like in a moment. But here it is. This is the result that I want. In other words, the rate at which the vector field strains, the rate at which the fluid strains is completely determined by this gradient of the velocity field. Is there any question that you have on this derivation? So what is important here is to know exactly what we're looking for. In this case, we're interested in the strain that the fluid undergoes. Because the fluid is constantly in motion, there is no unique strain to be considered the way that there was in the case of solids. In the case of solids, you have an initial configuration which is unstrained, you have a final configuration in which the system reaches a new equilibrium. You can discuss that strain in the final configuration. It's a single configuration. In the case of the fluid doesn't reach equilibrium when you apply these forces to it that cause it to move. It will continue to move, and so it will continue to deform, and therefore it will continue to strain. So there is no unique final configuration. You have an infinite sequence of final configurations. And so you need to introduce a new concept, which is not the strain, but the rate at which the strain takes place as the fluid moves. Right.
Sorry,
that's, yes.
Even as a case of the steady flow or stationary flow?
If it's a stationary flow, this will give you an answer 0.
Yeah.
Oh, no. Stationary is no time dependence. In the case of stationary flow, yes. You will have a strain rate. In a static flow, V is 0, and therefore there is no strain. So that is the first thing that you need to do. You need to quantify the strain in terms of your original elementary definitions that you developed for solids in the first year. You then calculate the rate, or you work out a formula for the rate at which the fluid strains, and then you apply that formula using previous result, or the result from the previous lecture that we had, which gives you information about the rate of vector separation of these fluid points. And the calculation that follows then delivers this result. So those are the three things that you need to isolate as logical units that you must understand. The derivation you need to know, and you must understand exactly why it is that you're heading for this formula. Right, the next step is to understand the content of this formula. So let me now look at the right-hand side. The left-hand side we've already interpreted physically. Let's now look at the right-hand side. This is interpretation. Of the right-hand side. So we have n hat dotted with lambda acting on the vector field V. What kind of quantity is this? Well, if you look at the left-hand side, delta L is a scalar. The rate of change of a scalar with respect to time is a scalar. Divided by a scalar, it's a scalar quantity, isn't it? So this is a scalar quantity. Let me write out in index notation what it is. Lambda, you remember, is d by dxi. It's it is the vector operator which you wrote in the first year as lambda is equal to d by dx I hat plus, or x hat, plus d by dy y hat plus d by z hat. So that's what my d by dxi indicates. It's the three components of this vector operator. It's convenient to abbreviate the derivatives with respect to a space coordinate by shortening the partial derivative symbol, and I will use the partial delta subscripted with the I to denote that derivative. So what we have here is, well, n dot nabla, this is nk, partial derivative subscript k. That is n dot nabla. It's an operator. It's a scalar operator. It operates on v, so it will act on the velocity components of v, and here you have the dot product. So this is now a vector quantity. You can see it has one free index. That makes it a vector quantity. And so when I dot it with another vector, I write it as n subscript I, because I'm dotting it with a superscripted quantity. This, I take it, is familiar to you from your tensors course. Right. So that's what it is. It is, if I drop the index on the I and drop the index, on the V, and raise it on the N just for convenience, I get this. And what I want you to notice about this is that it is made up of, first of all, a second-rank tensor. That second-rank tensor consists of the gradients of the components of the velocity field of the fluid flow. Right? I've written it here in covariant form. The vector n hat is not a property of the fluid flow. The gradient of the velocity is, but the n hats are vectors which I choose because I'm interested in the strain in a particular direction. And so they're not properties of the fluid flow, they are things, information that I put in, which determine the direction in which I'm considering the strain. So this is a property of the fluid flow. And these are determined by the direction in which we calculate the strain. So these are a choice by you, if you like. All of the information about the strain rate is contained in this gradient of the velocity field. All of the information that determines the strain is contained in here. Good. Well, now what I want to do next, for my next contouring trick, I want to show you that in fact this tensor contains too much information. We don't need all of that information to calculate the strain rates. But note that Ni and K is symmetric in I and K. In other words, this tensor product of n with n is a symmetric tensor. You also know that every tensor of rank 2 can be decomposed uniquely into a symmetric tensor plus an antisymmetric tensor. But also, di dk can be uniquely decomposed into a sum of symmetric and antisymmetric tensors. And the decomposition, I take it that you know it. The decomposition is given to you by di dk. Well, maybe I should preserve what I've got up there so that you don't get anxious. I don't want you suffering from angst in this class. You write this as 1/2 di vk plus dk vi plus 1/2 di vk minus, this is ki, so here this is ki minus di vk. So this is the symmetric part. This is the antisymmetric part. The third thing I want you to notice, recall, if you sum an antisymmetric rank 2 tensor with a symmetric one, the answer is 0. Have you proved this in your course on tensors? Let me give you a quick proof. Some of you seem a bit uncertain. There is a long way to do this, and there is a short way to do it. The long way to do it is to write it all out. And when it comes to tensor notation and index notation, if in doubt, write it out. It's a good principle to follow. If you don't understand what the expression means, write it out in full. Do this a sufficient number of times, and it will become second nature to you, reading it, unwrapping it, repackaging it, and so on. Anyway, that's the Dodo's way of doing this proof. So what I'll do is the slick proof. This is the slick version. Let Aij be antisymmetric. And Sij be symmetric. What do I mean by this? I mean that Aij is minus Aj. And the symmetric means that Sij is equal to Sji. What I want is to evaluate the quantity Aij summed with Sij. You can have the indices upstairs or downstairs, it doesn't matter which way around you have them. The indices can be seesawed by use of the metric tensor. Right, so the first thing I'm going to do is I'm going to use these two properties. So this means that I have minus Aj and plus Sji. Right? Which gives me, so this is by symmetry and antisymmetry. And this then gives me minus Aj Sji. But in a summation, the index, right, the role that it serves is simply as a placeholder. It's a bit like student. take a student out of the class, replace him with a completely different student, it makes not one bit of difference to the performance of the class. Right? That's what I mean by dummy index. And so what I'm going to do is I'm going to change the names of the indices. So I'm going to change the j to an I in the summation, and I'm going to change the I to a j, because this does not change the summation. Everybody happy with that? And now you see that you've got exactly the same thing on the right-hand side as you've got on the left-hand side, except for the sign. Take everything over to one side, and this means that 2 aij sij is equal to 0, and therefore aij sij is equal to 0. There is the result that I want. If you sum symmetric on anti-symmetric, you get 0. Everybody happy with that? Good. So I'm going to use this fact. Ni, Nk is symmetric. Partial k on Vi consists of a symmetric part and an antisymmetric part. And so, we apply this now. Nk, Ni, Lk, Vi is equal to Nk, Ni times 1/2 of dk Vi plus di dk plus Nk Ni 1/2 del k Vi minus del I dk. This is symmetric on antisymmetric. It is therefore 0. If you don't believe it, then write it out in full. Write out the two summations and laboriously remove the terms pairwise until you're left with nothing. And so this quantity here is Nk Ni times 1/2 dk Vi plus di dk. And that is what the quantity on the left-hand side evaluates to. So the message here is that the quantity that determines the linear strain rate, yes, okay, I construct it from this tensor dk Vi, but in fact I don't need the full tensor. I need only its symmetric part. Only the symmetric part of this tensor determines the strain rate. i.e., the strain rate is determined only by the symmetric part. Of dk Vi. Good, so what I'm going to do is I'm going to introduce some notation. Define. Now, books differ in these definitions by a factor of 2. And I always have a traumatic experience in trying to decide whether to include the factor of 2 or remove it. So, I think in my notes I included. Let me check. So so that I can be consistent. Yes, I include the factor of 1/2. Where is this definition? Yes, I include the factor of 1/2. So we define the tensor which we call Eij to be 1/2 dk vi plus di vk. A little bit inconsistently, I'm going to call twice the antisymmetric part omega ij. And you'll see the reasons for this a little bit later. So this will be, I'm sorry, there's an inconsistency here. This is ki. And this must be ki. And I'm going to define this one to be dk vi minus di vk. No factor of 1/2 in that one. So what it means is that dk di is going to be eki plus twice omega ki. These are just shorthand symbols for the symmetric and the antisymmetric part. There is no deep significance in them.
Sorry?
Yes?
Why is omega twice not why is the true part of the omega not?
Why do I not put the 1/2 in here?
I mean in the dkvi, the last definition.
Oh, it's 1/2. It's because I'm an idiot. You want that?
Yeah.
Is that right? That means you're not an idiot. I am. All right, do you have any questions on this? So essentially what this tells you is that the linear strain rate is completely determined by this tensor that I've called Eij. So 1 over delta L d by dt of delta L is then equal to Ni nk, let me write it the other way around, it's Eik Ni nk. Any questions on this?
Did you just, we introduced omega just for completeness, we're not actually using it.
Yes, we will be using it a little bit later in maybe the next or the lecture after that. You can see already what it is. You recognize it?
Maybe after that cup of coffee.
Another strain rate that you consider in elementary physics, maybe not so elementary physics, because normally you do this only when you begin your studies of thermodynamics, but you consider the volume expansivity in thermodynamics. As the fluid moves, in general, it will change its volume, won't it? If it's a liquid, then the volume of a given fluid element will always be the same, because the liquid is, to a very good approximation, incompressible. But a gas can expand and it can be compactified. So if you put it through, take a gas flow and force it into a constriction, you will be compressing the gas. The volume of the fluid will change as the fluid moves. So the next question is, at what rate does the volume of the fluid change? This is the volume expansion rate. Right, well, the first thing we need to do is learn how to describe volume. But I take it that you've already done this, so I won't spend too much time on it. You've done it in second and in third years, and probably now in the course again. So let's consider a cube of fluid material. At time t. Actually not a cube, I want a rectangular parallelepiped. So let's put that in. Isn't ideal or easy? Well, parallelepiped, I think it is. So what I've got here is something which is spanned by three vectors, which I will call imaginatively capital X1, X2, capital X3, and the one that I'm considering is that one. So as the fluid moves, now I need a bit of artistry. So as the fluid moves, that origin will move into a new position, and each of the vectors will move into a new position, and in general these vectors will have skewed. Not going to work, is it? How do I draw it? It's very interesting to do it like that. The vectors skew. So your volume deforms. And because we're watching it for a very short period of time, delta t, these vectors will have skewed slightly, and the vectors themselves will remain approximately straight. So the volume of the original parallelepiped. Do you remember how to calculate volumes? Okay, it's base area times height, isn't it? You can convert this into a vector formula. So you do the dot product of x3 with x1 crossed with x2. Yes? And you know that you can write that volume as a determinant, because the vector product can be written as a determinant, and the dot product simply replaces the ijk. So this is basically a determinant, and I take it that you know that the determinants are written. Okay, so let me write out the components of the vectors here. I will write the label that numbers the vector as capital A at the bottom, so that you don't confuse it with components. And the components of the vector x, A, will be given to me by this, where the capital EI's are I, J, and K. So this is a shorthand for x1, A, times x hat, plus x2, A, times y hat, plus x3, A, times z hat. So that's how I get to write the components. And then my volume is going to be epsilon I, J, K, xi, 1, xj, 2, K3. Is this formula familiar to you? No?
Yes.
So there's a mixture of yeses and nos?
Yep.
So the ayes have it, and the nays come talk to me afterwards. Okay. So at time t dashed, the fluid points, let's call this t plus delta t. The fluid points occupy volume V dash. The volume of strain is defined by. So it's the same formula as we had for the linear strain, except that now you put volumes into it. The volume strain is defined by V, the new volume minus the initial volume, divided by the initial volume. So the volume strain rate is V dashed minus V over V times divided by delta T. Volume strain rate is, and what I now do is take the limit as delta T goes to 0, and my volume strain rate becomes, the initial volume is a constant. What changes is the final volume and the time delta t, so this is the limit of delta t goes to 0, or v dashed minus v over delta t, and you see that this is 1 over v dv. Why the capital D's? Why the material strain rate? Well, because I'm measuring the volume as I move with the fluid. Right, so let me set up the calculation, then you will need an ample supply of coffee to cope with the next lecture. I will then release you to have the caffeine injected intravenously, and you can come back and tackle the calculation itself. The first thing I want to do is to rewrite more conveniently that formula for the volume. Rewrite V as. Now, it doesn't really matter what happens if I exchange the order in which I do the cross products, this triple product. X1 cross X2 dotted with X3. What happens if I switch the order of the vectors?
The epsilon might be changed.
You pick up a minus sign, don't you? Changing the order of the vectors is like changing the order of the columns in the determinant. And so you pick up a minus sign. So if I want to release myself from the imposition that I must take x1, x2, x3 in that sequence, all I need to do is introduce a factor to compensate for the change of sign, and V can then be written as epsilon A B C is equal to epsilon I J K x I A x J B x K switching the order of the factors appears in the epsilon on the other side. All right, and so d by dt of v, the epsilons, well, these are just constant values, aren't they? They will be either plus ones or minus ones, depending on what indices you have on the epsilon. And so they act like constants in the differentiation. And then on this side, you get I, j, k, and you've got a product of three vectors, and so this will be d by dt of x, I, a, x, j, b, x, k, c, plus epsilon I, j, k, x, I, a, d, x, j by dt, x, x, j, b, x, k, c, plus epsilon I, j, k, x, I, a, x, j, b, d, x, k, dt. That's the x, k, c. Right, the next step is obvious. This is where you need to be caffeinated to cope. So we will break for 10 minutes. My watch says 5:02, and therefore we will recognize when my watch says 5 past. In the next part of the calculation, what we have to do is evaluate these bracketed quantities. And the way that we do it is by applying the result that has now been worked out, which I have on the board, which is that d by dt of xa is equal to xa dotted with lambda on d. If we want to convert this into components, then d by dt, because we're working with Cartesian components, this is simply d by dt of xi subscript a, and this then becomes xk. No, let me not use k because I'm using s a ds v I. Right, so this is what we now put into here. So this one over here is x s a ds v I. This one over here is x s b partial s on vj. And this one over here is x s c ds v k. So let's put in those expressions. Epsilon I, j, k, x, s, a, x, j, b, x, k, c, d, s, v, I, plus epsilon I, j, k, and it is x, I, a, x, s, b, x, k, c, ds, vj, plus epsilon I, j, k, x, I, a, x, j, b, x, s, c, ds, v, k. what I now, yes? Someone? No? What I'm now going to do is I'm going to multiply both sides by epsilon superscript ABC and sum, right? And I use the fact that epsilon RST, epsilon RST is equal to 3, and so we get that dV dt times, now this is epsilon ABC, epsilon ABC. I'm getting rid of the epsilon, in other words, on the left-hand side, and that gives me, on the right-hand side, epsilon ijk, epsilon ABC, x S A X J B X K C D S V I plus. Can I leave you to write out the other terms? The same thing happens in each of the terms as happens in this one. If you now look at this one over here, this is the determinant of the components of XA, XB, and XC. Is it that? And therefore it gives you the volume, V. So this is V times epsilon S J K. Same thing happens in each of the two remaining terms. I now have V times epsilon ijk, epsilon sjk, del S dI. And I use, this is the epsilon summed over two indices, right? And the epsilon summed over two indices gives you 2 factorial. Delta S I. And so here I get 2 factorial times V. Now delta SI summed on partial ds VI gives me delta S VS. And each of the remaining terms delivers exactly the same answer. And so what I get is that dV by dt times 3 factorial is equal to 3 times 2 factorial V. What is ds Vs? Well, it is dV1 by dx1 plus dV2 by dx2 plus dV3 by dx3. And this is just the divergence of the vector field. Three times 2 factorial is 3 factorial. And so what this tells me now is that dv dt times 1 over v is equal to divergence of v. This is the origin of the definition of the divergence of a vector field. It is also the physical interpretation of the divergence of a vector field. So what the divergence measures is the rate at which the volume of a moving fluid is increasing divided by the original volume. It is the volume expansion rate of the fluid as it moves. That is what the divergence measures. You will probably have been told by some misguided lecturer in your undergraduate years, you know, they draw a point charge like that, and they say, you see the arrows diverging, and that's why we call it the divergence. That is a delightful piece of ignorant nonsense. I'll tell you why it's a delightful piece of ignorant nonsense. First, at the point where the charge is, the field is undefined, and therefore the divergence is infinite. It's undefined. Right? If you work out the divergence at any other point, the answer is 0. There is no divergence in this field at every other point except the origin where it is undefined. And so this is not a picture of what the divergence means. Here it is. This is the true significance of the divergence. The divergence measures the rate of expansion of the volume occupied by a fluid element as it flows with velocity field v per unit volume. Rate of expansion per unit volume. Happy? You should be. Interestingly, this divergence of the vector field is what? It's also calculated from the tensor EIJ. If you contract the I and the J on this tensor, this is, what is it? Well, it's 1/2 di Vj vi plus di vi, and so that is di vi, and that is the divergence of v. So what I'm telling you by going through this little exercise on the side there in a minute is that this volume expansion rate is also completely determined by the tensor EIJ. Right? It's the trace of that tensor. You have a question?
Could you please explain what you mean by contracting?
Contraction of indices. Have you not done this in the general relativity?
No.
Oh, all right. But you've done raising and lowering of indices. Am I right?
Yes.
Yes. Okay. So, if you have so let's take the tensor product of two vectors, ai, bj, or any tensor with two indices, I and j. What you can do is lower one of the indices using the metric tensor. And so you can define that this is a covariant tensor of, a contravariant tensor of rank 2. You can change the position of the index. In other words, you can construct a tensor of a different covariant rank and contravariant rank from a given tensor using the metric. So I can construct from this a tensor which I call Tij, which is Ti Rg Rj. That is the definition of how you lower the index. You can also construct a mixed tensor where the first index is in the bottom position, the second index is in the top position from your contravariant tensor, and this is then, I've lowered the I, so this is Rj G Ri by definition. You can lower both indices. This will be GIR, GJS, TI, TRS. So given a tensor with indices in any position, you can construct using the metric tensor mixed tensors or tensors of different varieties but with the same rank where the indices are in different positions using the metric tensor. Right?
All right.
Okay, now, contraction of indices. This is a generalization of what you do when you do the dot product. So when you do the dot product, A dot B, the dot is a shorthand, it is a classical shorthand for the metric tensor. You are working out the value of the metric with inputs A and B into its arguments. So this is G of A and B, like that. And you write it in component form as G, I, J, A, I, B, J. Right? You happy with that? You can now use this raising and lowering set of operations to combine the G either with the A or with the B. So you can drop the index on the A and write this as A, J, B, J. Or you can combine it with the B, in which case you drop the index on the B, and this then becomes AI, BI. Right? So you can form the scalar product from two vectors by dropping the index on one of the vectors and summing over a lower index and an upper index. The process of summation over a lower index and an upper index is called contraction. It's called contraction because what was originally a tensor of rank 2 has had its rank lowered by 2. You've contracted the number of indices in other words. That's why we call it contraction. And okay, so this is for a rank 2 tensor that is formed as the tensor product of two vectors. You can apply this to a rank 2 tensor of any kind. If you take a rank 2 contravariant tensor and form the mixed tensor where one of the indices is in the lower position, what you can then do is sum over these indices and form the scalar TII. And that is called the contraction of this tensor, or of that tensor, or of any other of the forms that you can get from it. It's a contraction because you've summed out two of the indices and you've dropped the rank of the object by 2.
So we use the metric tensor when we are contracting.
Yes. I don't know how much geometry you know, but in the absence of a metric tensor, there is no relationship between covariant and contravariant objects. No relationship at all. The kind of geometry where you study that is called a fine geometry. in the case of geometry where you have a metric as well, in other words, in any form of metric geometry like Euclidean or Riemannian or Minkowskian, then you have a metric. The metric can be used to define a unique relationship between covariant vectors and contravariant vectors, which doesn't exist in the general case. And that unique relationship is what is responsible for this kind of index gymnastics that they teach you in relativity. Does that answer your question?
Yeah.
Any other questions? All right, so we've done linear strain rate, we have done volume strain rates. We've discovered that both of those strain rates are described by the tensor, which I called Eij, which is 1/2 di Vj plus dj vi. In other words, it is the symmetric part of the velocity gradients. Let's now consider one final strain rate, which is introduced in elementary physics, and it is the shearing of an object. So the section is called shearing rates. Just to remind you, in the elementary shear, you take an object, in the case of elementary physics, which is where this concept is introduced, you take a solid object, elastic, or something that has elastic behavior, and you force it into that position by applying a force F to the top and the bottom faces. This is a three-dimensional object, of course. I've just drawn the cross-section of it. You apply forces to the top and bottom of the object in opposite directions and tangentially to the surface. And it will produce a deformation of this kind here. A deformation of this type is called a simple shear. And you measured the simple shear by talking about the angle, I'll call the angle alpha there, the angle by which the vertical face relative to these forces moves in the deformation. So the shearing strain was defined to be the angle alpha. Now, if you do this to a fluid, supposing you have a layer of fluid, and you apply forces which are tangential to the top surface and the bottom surface, the fluid will not stop moving. It will continue to move as long as the forces are applied. Forces applied like this, incidentally, are called shearing forces, and the fluid will simply yield. It will not resist shearing. This is what makes the fluid a fluid. And so we have no final configuration to discuss, the way that we do in solids. We have a continual deformation as long as the forces are applied, and so we introduce the concept of a shearing rate in a fluid. And that's what I want now to discuss. So the shearing rate, I'm going to use not this angle alpha, I'm going to use the complementary angle theta, because you can see why in a minute, in terms of the mathematics. The way that we can define the angle theta, which is pi minus alpha, pi by 2 minus alpha rather, is by taking unit vectors in the directions of the sides of this object. So I'll call the unit vector vertically 1, n1, the unit vector horizontally n2, and these will then deform. n2 will remain unchanged, but n1 will deform into position n1 dashed. So in time t, n2 remains unchanged, N1 deforms. And what I'm going to do now is write the angle theta in terms of the dot product of the vectors. And use the fact that n1, the magnitude of the vector, is 1, n2 is equal to 1, and so it gives me a formula for theta. Cos theta is then n1 hat dotted with n2 hat. So, in a simple shear, N2 remains fixed. In a general shear, N2 may change. So I want to consider the rate of change of the angle theta. This means that I work out d by dt of cos theta, and this will then be d by dt of n1 hat dotted with n2 hat plus n1 hat dotted with d by dt of n2 hat. d by dt of cos theta is minus sine theta, d theta by dt. And now I use my formulae that determine the rate of change of the unit vectors, or of any vector, and that is that this is n hat 1 dotted with lambda acting on v, dotted with n2, plus n hat 1 dotted with n hat 2, dotted with lambda acting on v. And so that gives me, now the first formula says that this is n1k dk on vi n2 I plus n I1 multiplied into n2, this is n2k dk di. Take out the ni1, ni2, and if you now change the indices, so this is ni1, I've got an nk1 there, change this index to k, this index to k, that index to I, that index to I, and you see that I then have a common factor, which I can write as nk1 ni2 into dk di plus di dk. The important point to note here is that this rate of change of the angle theta is determined completely by my tensor dki. And this is twice that tensor. In fact, you can rewrite this formula symmetrizing this expression, the nk1 ni2, you can symmetrize and write it as 1/2 nk1 ni2 plus nk2 ni1 times 2 eki. The reason for that is that eki is symmetric, and so the antisymmetric part of this tensor n1, n2 will, when summed over a symmetric tensor, will die. And so this gives you the symmetric part of nk1 ni2 plus n2k ni1 times eki. The important thing to note here is that the rate of change of the angle theta, which is related to the rate of change of the angle alpha, and therefore is a measure of the strain rate, is determined by the tensor eki. Again, it is the symmetric part of the velocity gradients. I don't want to make too much of that. You can read what I've got in my notes here in order to see how to make use of it. Do you have any questions on it? So the message of all of this is that the elementary strain rates are all determined by a single tensor, all strain rates are determined. Dij, which is 1/2 dk plus dk. I need to introduce to you just one final concept before we move on from the strain rate of fluids, and it is the concept of pure shear. What I introduced to you there was what I called simple shear, and in a simple shear you can see that when you shear the object in a simple shear, you are not just deforming the object, you are also rotating it, because the center of mass, or the geometrical center, if the density is uniform, it will also be the center of mass. The geometrical center shifts in the shearing operation. You have a rotation of the material as well as this shearing deformation. So the concept of pure shear is where you have the shearing action without rotation. You also have a change in general. In this picture here, you have no change in volume, but in a general shear, you do have a change in volume. And so it's convenient to introduce also the concept of shearing without volume expansion. And that is what I now want to do. All right, so the way that we do this is we consider the symmetric tensor Dij. The contraction of this tensor is E, I, and that is given to us by D, I, V, I plus D, I, V, I, and that is lambda V, and this is equal to 1 over V, delta V, D delta V, dt, which is the volume expansion rate. So what this tells you is that if our tensor Eij does not have zero trace, then there is a volume expansion. This represents a volume expansion rate in the shearing process. A pure shear is one where the volume remains constant. It is a shear in which the volume remains constant. i.e. I is equal to naught. This is not true in general. So we decompose a shear rate into the sum of a pure shear rate, which I think in my notes I call capital D, D and J into sort of the pure shear and a volume expansion. So how do we do that? The answer is, what we need to do is write Eij in the general case as a sum of Dij plus lambda dot V. Oh, but I can't just have lambda dot V there, can I? I don't have any indices on it. The indices are summed out. So I will need to multiply this by, yes, I need something with two indices. And it's got to be something which is determined not by the fluid flow, but is a property of the geometrical structure in which the fluid is flowing. Oh yes, I've got a metric tensor, haven't I? So what I do is I put in a Gij here, which in Cartesian coordinates becomes delta Ij. And I don't know quite how this sum is going to work. In fact, let me not even do that. Let me write this as, yes, I'll leave it like that. So put a lambda in here because we don't know how this decomposition is going to work out. And for reasons that will become obvious in a few lines, I want a factor of half introduced over there. So this is the definition of Dij. This is an implicit definition dij together with the fact that we want. Dij must be a pure shear, and so dii must equal naught. So these two equations together define the d that we're looking for. So the question is, what does this d look like? The answer is very simple. What we do is we trace or contract this tensor E . When you lift the index on the G, you get a Kronecker delta, the mixed Kronecker delta. And so that is what you get. This one must be naught. The Kronecker delta is, well, it is delta 1, 1 plus delta 2, 2 plus delta 3, 3, because we're working in space, and that gives me 3. Right? And this is lambda v. And so lambda must equal, so that is lambda v goes out, so that is 3 lambda is equal to 1, and therefore lambda is equal to 1/3. I think I've done that correctly. And so dij is then eij minus, what's the expression? 1/2 of that is equal to eij minus 1/3 and the gij. If you prefer to rewrite this without the 2 on the left-hand side, then this becomes di vj plus dj vi minus 2/3 and the gij. So this is the tensor that describes pure shear. Nabla v is often written as theta, and it is called the dilatation rate. So what this tells you is that the shearing rate tensor, eij, can be broken up into the sum of a pure shear, dij, defined by that expression, plus the dilatation rate. All right, that completes what I want to say on the shearing rates. What I will do in the next lecture is interpret the omega ij's that I have used for you and show you that this describes the way in which the fluid rotates. We have a tutorial today, I think. Today is Wednesday. Is today Wednesday?
Yes.
Yes. So we have a tutorial at, is it 2 o'clock? From 2 to 4? In which room does that occur?
Here, probably.
In here, all right. So I will see you this afternoon. I've sent out the tutorial. I sent it out yesterday, so please attempt the questions before you come to the tutorial, otherwise it is a meaningless exercise.
Yeah, it doesn't seem like any of us got the email with the tutorial.
I sent it out yesterday to the NASP 2012 email address. Nothing? You've not had versions of the second version?
Second version of the notes.
You've received the notes,
Yeah.
but you haven't received the tutorial, no? All right, I'll send it out now. Is tomorrow's 2 o'clock session free? No. I think it's probably best to have the tutorial today then, but please try to do at least one of the questions before you come to the tutorial.
2 hours free today between 11